So this is section 2 for day 2. What I would have done in class on Tuesday when we were talking about taking the derivative, and we learned on Monday the product and the quotient rule. So now we are learning when you look at a function how to know if you need the product or the quotient rule or if you can get around it, and that's what this is about. So this is one of the 2 worksheets for today, and you can find them in Angel. The first one we are looking at is a particular function, and what you want to remember is when the denominator is a monomial, that means that you do not need the quotient rule. Even though this looks like a quotient, we don't have to think about it as a quotient. So this 3 in the denominator, there's 2 different ways to think about it. One way would be to write it as x squared over 3 minus 7x over 3. But the faster way to think about it is to think about there being a 1 up top and pulling the 1 and the 3 out as a constant multiple. So I'm rewriting the function from how it looks like a fraction to being 1/3 times a polynomial. And constant multiples mean when you take the derivative, they can just come along for the ride on the derivative, and then you take the derivative of x squared, which is 2x, and 7x, which is 7, and that would be the fastest way to do the derivative of this problem, rather than using the quotient rule when it's not needed. We've done ones like B over and over again, so this is just a quick review. When you look at 7x to the 5th over 5, you want to think about it as 7/5 times x to the 5th. So it's the same idea as A, except it's not a binomial. And I'm going to pull the 5 down to take the derivative and get 7x to the 4th. So even though it looks like a quotient, I don't need the quotient rule. The same thing is true on C. You can look at the -3 and the 5 and pull that out to be a constant multiple, -3/5. And then you can think about the 7x over x and the 5x squared over x. So just to be really deliberate about it, you're pulling the -3 and the 5 out as a constant multiple, and then you're going to simplify the 7x over x to be 7, and the 5x squared over x to be 5x. This is, again, a rewrite of the function. You're not taking the derivative yet, you're just rewriting it so that it's easy to take the derivative. And then all you have to do is leave your constant multiple where it is and take the derivative of 7, which is 0, and -5x, which is -5. And when you multiply that all out, you find out the derivative is -3. So it's a different way of looking at the problem. And you do it when the denominator is a monomial. That's the key to when you can do this. For D, same idea. The denominator is a monomial. So you can think about 9/5 as a constant multiple, and the degree on x is -3 because it's in the denominator. You pull the -3 down, multiply to -27/5, drop the degree to -4. Rewrite your answer, -27 over 5x to the 4th. For E, I can't think about 8/2 as a constant multiple because there aren't parentheses around this like there were in C. The difference between C and E is the parentheses there. So without the parentheses, I'm not going to be able to have a constant multiple. I'm going to have to just write it as 8x squared over 2 square root of x minus 5x over 2 square root of x. As I don't have a constant multiple in the numerator. So then that rewrite looks like 4 when you divide 8 by 2, x to the 3 halves when you subtract 2 minus a half, minus 5 halves, which is your constant multiple here, and then 1 minus a half is 1 half. So I've rewritten my function so I don't have to use the quotient rule, and then I can just use the simple power rule. Pull the 3 halves down and get 6, drop the degree to a half, pull the 1 half down and get 5/4, drop the degree to negative 1 half. This is when you have a choice. You can choose to put this x to the 1 half in the denominator here to simplify. But the better option is to pull out the lowest degree on x and pull out any fractions that you can. So we're going to practice that because it's an important idea. So we're going to pull out x to the negative 1 half, and then we're going to pull out a 1/4 as well. So when we pull out the 1/4 and the x to the negative 1 half, we are going to be left with thinking about 6 as 24/4. So we'll be left with the 24 part of the 6, and we'll be left with x to the 1 half minus negative 1 half, which is 1. And then minus, pulling a 4th from 5/4, I'll be left with the 5. And negative 1 half minus negative 1 half is 0. So that's it, just the 5. So I'll write my final answer as 24x minus 5 all over 4 square root x. So the 4 from here is in the denominator. This is a negative exponent. It belongs in the denominator. And there's my numerator. Problem F. So for problem F, I have something that looks like I need the quotient rule because the denominator is not a monomial and I've got a function on top and a function on the bottom. However, if you think carefully about this problem, x squared minus 9 over x plus 3, you can factor x squared minus 9. And if you do, you can see that the x plus 3 and the x plus 3 can divide each other out if x is not negative 3. Okay, that they do not divide out if x takes on the value negative 3 because then they'd both be 0 and they would divide each other out. So if x is negative 3, the whole thing's undefined. But as long as I make that distinction, I really can think of my function as simple as x minus 3 if x is not negative 3. And then the derivative of that is even simpler. It's 1. The derivative of x is 1. The derivative of negative 3 is 0 if x is not negative 3. So you can go ahead and do the quotient rule on it, and you'll find that same answer. But if you can factor to simplify before you start, it's always easier, and it makes the difference in a test sometime because sometimes time is of the essence, and if you do the quotient rule, you're going to spend a lot of time. Okay, flipping to the back page, G. Here's another example of where knowing how to factor can save the time you need on a test to get the grade you want. Because I would have to do the quotient rule on these two functions if I didn't know how to factor it. But because I know how to factor the difference of 2 cubes, which is something that you should know, and then I can divide out the t plus 2, I can think about my function as 1 over t squared plus 2t plus 4 if t is not negative 2. And why is this function better than that function? Well, the answer is this 1. That's one of my functions now, and it's an easy function, and its derivative is 0, which is even easier. So if I do the quotient rule on this, it's going to be a lot faster than doing the quotient rule on the original problem. And eventually we'll learn that we don't even need the quotient rule. We're going to learn another rule to deal with this. But for now, I'm going to square the denominator, start with the denominator, which I really didn't even need to write because I'm going to multiply it by 0, which is the derivative of the numerator. And then the numerator is 1, and the derivative of the denominator is 2t plus 2. So my final answer is, this is all 0, so I'm getting negative 2t minus 2, if I want to distribute that negative 1 through, and then t squared plus 2t plus 4 squared. That's my derivative. A lot faster than using these two and trying to simplify it. H. When I talked about the quotient rule yesterday, I said use it, I'm sorry, not the quotient rule, the product rule. I said use it all the time to get used to it. I'm going to go back on that now that you know how to use it, and I'm going to say if you have x squared minus 3x times 1 over x cubed, don't use the product rule. Distribute so that you get a function that you don't need the product rule for. So distribute and rewrite your function as x squared times 1 over x cubed. If you subtract your exponents, you're going to get 2 minus 3, which is negative 1. Then negative 3x times 1 over x cubed. If you subtract your exponents, 1 minus 3, you're going to get negative 2. So we're going to have minus 3x to the negative 2. Rewriting my function like that, I can take the derivative. Negative 1 moves down, the degree drops to negative 2. Negative 2 times negative 3 is positive 6, and the degree drops to negative 3. And then I can pull out x to the negative 3 and be left with negative x plus 6. And finally, I can write it as negative x plus 6 over x cubed. That is my derivative. Same thing for I. You could use the product rule, this being your f and this being your g, but if you don't have to, it's a little better to distribute through and avoid it. So I'm going to add my exponents when I distribute and get x to the 4/3, and I'm going to take x, the cube root of x, which is x to the 1/3 times 1, and get x to the 1/3. So that's my function. Its derivative is 4/3 x to the 4/3 minus 1 plus 1/3 x to the 1/3 minus 1. Because my exponent here was less than 1, I went negative. So I'll simplify it by pulling out the 1/3 that they both have and the lowest degree on x, and I'll be left with 4x, the 4 from here, and 1/3 minus negative 2/3 is 1, x to the first, plus 1. Because I pulled all of this out, I have to put 1 there to hold the spot. And then rewriting it as 4x plus 1 over 3x to the 2/3. So distributing to avoid the product rule. For J, my function is x plus 1 over the square root of x. This is a monomial, and so whenever that's true, whenever that's the case, I can rewrite my function as x over the square root of x plus 1 over the square root of x. I can rewrite it so that I get, subtracting my exponents, x to the 1/2 plus x to the negative 1/2. And I'm avoiding the quotient rule. I take the derivative with the power rule. So So I get 1/2 x to the negative 1/2 minus 1/2 x to the negative 3/2. And again, I'm going to pull out the 1/2 and I'm going to pull out the lowest degree, which is negative 3/2. And then I'll be left with an x here. When I subtract 1/2 minus negative 3/2, I get 1. And 1 here, because I pulled everything out. So my final answer is x minus 1 over 2x to the 3/2. And the last problem is K. And it's here to make a point that just because x squared minus 1 factors, it doesn't mean it's going to make the problem any easier. So unless I have a factor up top of x plus 1 or x minus 1, the factoring does not help me. So factoring won't help. The denominator's not a monomial. And so in this case, I have to use the quotient rule. I don't have a way around it like I did in the other ones. And sometimes that's the case. But you always want to check, because if you can avoid it, you'll save yourself time. But the quotient rule says square the denominator, start with the denominator, take the derivative of the numerator, which is 4x cubed, minus the numerator, x to the 4 plus 3, times the derivative of the denominator, which is 2x. And so I have to simplify that in order to have my derivative in a form that I'm going to be able to use it. And simplify means distribute here, 4x to the 5th minus 4x cubed. Distribute here and remember to distribute your negative. So minus 2x to the 5th minus 6x all over x squared minus 1 squared. Never a good idea to FOIL this out. There's never a reason to do that. The only thing you want to FOIL out or distribute out is things that you are going to be able to simplify with subtraction. So I'm going to distribute the numerator. I'm going to leave the denominator as it is. And I'm going to end up with 2x to the 5th minus 4x cubed minus 6x all over x squared minus 1 squared as my final answer. So I had to use the quotient rule in K. You want to be able to use it if you have to, but try to see when you can avoid it. So that was worksheet number 1. Worksheet number 2 from this section is also on Angel, and its sort of nebulous name is more types of problems. But the goal of the last worksheet was to try to figure out the fastest way to do the problems. The goal of this worksheet is to remind you that the problem may be asked in a way that you need to understand the vocabulary of it. So for example, number 1, find the equation of the line tangent to the curve x squared minus 7 squared at the point negative 136. So what I'm trying to do is find an equation of a line. So from that point part, I want to remember the point slope form of a line and plug in everything that I know right now. And right now I know x1 and y1. So I can put in y minus 36. I don't know the slope, so I'm going to put a little box there. But I do know that x minus negative 1 is the same thing as x plus 1, and I can write that much of the answer. But in order to figure out the slope, I need to figure out the slope of the tangent line at the point negative 136, and that requires the derivative. So y prime will give me the slope of the tangent line. And I need to find y prime. But in order to find y prime, I've got to rewrite, just like on that last sheet, I've got to rewrite y. by foiling it out, because we don't know how to take the derivative of a function squared. We don't have a rule for that yet. That's coming on Wednesday. But we do know that we could FOIL it out to be x to the fourth minus 14x squared plus 49. And when it's rewritten like that, we can take the derivative with the power rule. Pull the 3 down, drop the degree to 3. Pull the 2 down, drop the degree to 1. Derivative of 49 is 0. And so that derivative is going to help us figure out this slope. Because when x is -1, which is the point that I'm talking about, the slope will be 4 times -1 cubed minus 24 times -1. And so it will be -4 plus 24, which is 20. And that's what I want to put in my box here, 20. So for me, that's fine. That's the equation of a line. Sometimes WebAssign wants it in slope-intercept form. So we'll take a minute and distribute our 20 through and add our 36 and put it in slope-intercept form, just in case they need it that way. So we use point slope. The derivative helps us get the slope. We got the equation of the tangent line. The same thing's true in number 2. I'm going to do the same thing, so I'm going to say y minus 0 equals some slope times x minus 1, all because I want the equation of the tangent line at this point. So I can do that really quickly. But in order to get the derivative, which is going to give me this slope, I have to think about this function and see how confusing it is. This is one function times another function divided by a third function. There's 3 functions going on there, and there's multiplication and division, which would mean a product rule, and in the middle of it, a quotient rule. Definitely don't want to think about the function that way to take its derivative. So I'm going to do a rewrite, and I'm going to keep the denominator, but I'm going to multiply the x plus 2 and the x minus 1. Because remember, this function is like x squared plus 2 over 1. So if I wanted to simplify it, I could multiply the x plus 2 times the x minus 1. And that's what I'm going to do. FOIL that out to get x squared plus x minus 2. So yeah, x squared plus x minus 2 is a more complicated function than any of these 3. But when you look at the whole thing, now I just have a function divided by a function. I only need the quotient rule. I don't need the product rule along with the quotient rule. And that's what makes this easier. So my derivative is square the denominator, start with the denominator, derivative of the numerator is 2x plus 1 minus the numerator times the derivative of the denominator, which is just 1. And I can take some time and simplify this out, but realistically, I only want the slope at one particular point, so I'm going to just go right ahead and plug that x value in and save myself some time. Because depending on the problem, if I want a general rule, then I should simplify it. But if I only want the rule at a particular point, once you've got the derivative by using the quotient rule, just plug the x value in and then calculate it out. So I'm going to get 2 times 3, which is 6. 1 plus 1 minus 2 is 0, so that's all 0. 2 squared is 4. My slope is 3/2. And that's what I'm going to go back and put in here. And I can leave it like that, or I can distribute my 3/2 through. However you want to leave the answer, or however WebAssign tells you to leave the answer. So 1 and 2, the same kind of problem, just different derivatives that you had to take. Number 3 is a totally different type of problem. It says, where is the tangent to the curve horizontal? Well, that's not the same idea as tell me what the slope is when x is 6. This is more, what value of x should I plug in so the slope is 0? A horizontal tangent means the slope is 0. So I need the derivative of this function to be 0. And I got to figure out what value of x makes that true. So the first thing to do is figure out what the derivative of the function is. And again, the denominator is a binomial. I can't factor anything. I need the quotient rule, so I'm going to use it. Square the denominator. Start with the denominator, derivative of the numerator, minus numerator, derivative of the denominator. And then I'm going to simplify it, because I don't have an x value to plug in. I have to simplify it. So I'll distribute this through and get 2x squared plus 6x minus x squared all over x plus 3 squared, which is x squared plus 6x all over x plus 3 squared. So that's my derivative. Where is that derivative 0? Well, then algebraically I need to take it and set it equal to 0. Now, the most important thing to understand in algebra at this stage is how can a fraction be equal to 0? The only way a fraction can be equal to 0 is if the numerator equals 0. I don't even care what the denominator is. Although if the denominator is also 0, 0 over 0 isn't 0, so that's a problem. But in order to figure out what value of x could possibly make this 0, I need to look at the numerator. And so I want to know when x squared plus 6x is 0. And hopefully you remember from algebra class, the only way to do that is to factor out an x, and then look at the two factors that you have, x and x plus 6. So that means that if x is 0, the whole thing will be 0, and if x is negative 6, the whole thing will be 0. Neither of those two values makes the denominator 0, so I don't have to worry about that. To write your final answer, though, write the point that we're talking about on this curve. So x is 0, plug 0 back into your function, 0 over 3, that's the point 0, 0. Negative 6, plug it into your function, 36 over negative 3, negative 12. Where is the tangent horizontal? At these 2 points. Because if you plug the x value of these 2 points into the derivative, you're going to get 0 out. It's a different question than the first two. And that's why I spend so much time getting you to factor things out, because to answer this question, you need to factor out your derivative. It's the only way you're going to be able to figure it out. Number 4, the beginning of the general questions. These tend to cause some issues, so I wanted to make sure I gave a couple examples. If I tell you that f of x, some function, is always 7 minus another function, and then I ask you for the derivative of the first function when x is 4, that's what f prime of 4 means. Without knowing what the functions actually are, it's hard to answer this question without just using the rules that you know. And so this rule would be the difference rule. If you want to take the derivative of a function that's the difference of 2 other functions, all you do is you take the derivative of each and subtract them. So the derivative of 7 is 0, and the derivative of g of x is g prime of x. You can't be any more specific than that because you don't know what that function is, but you can call its derivative g prime. And now if I want f prime evaluated at the number 4, it's going to be 0 minus g prime evaluated at the number 4. Well, I don't know what g is, I don't know what g prime is, but I do know what g prime of 4 is because it was given to me in the problem. And it will always be given to you in the problem. So it is -5. And so 0 minus -5 is 5. And that's what f prime of 4 is. So even without knowing what the particular function is, you can use the rules to come up with your answer. And then, so why did I give you g prime of 4, or g of 4, I'm sorry. I needed to give you g prime of 4, you needed that. But why did I give you this? It's just to be confusing. You don't need it. It doesn't matter what the function is at 4. I needed the derivative of the function at 4. So this is called extraneous information, and they'll throw that in there to try to be confusing. Don't worry about it. Just use your rules, and whatever values you need, go up and grab them. Another example, the last problem that we'll do is another example of that same idea. You have, I'm going to write general rules too, just so we remember what kind of problem this is. You have a function, h of x, that is equal to the product of two other functions. Remember when you write f and g next to each other with nothing in between? That is a product. So that you need to take two functions and multiply them together, and that gives you what h is. Then they're asking you for h prime of 4. Well, in order to get h prime of 4, you have to first figure out h prime of x. That's going to be always the case. So to get h prime of x, you have to look back up at your rule of what h is and say, oh, the product of two functions is going to be the product rule. So I'm going to write out what the product rule says. I have to have it memorized to do that. H of x is the first function times the derivative of the second function plus the second function times the derivative of the first function. This is the product rule, and you have to know it in general, not just specifically how to plug in. You have to know the product rule in general. I don't know why this is becoming so unclear, but hopefully as I'm saying it, you can write it down yourself. So f of x times g prime of x plus g of x times f prime of x. So h prime of 4 is f of 4 times g prime of 4 plus g of 4 times f prime of 4. It's the product rule, except everywhere I had an x, I put a 4, because I'm trying to evaluate at this point. And I don't know what these functions are, but I know what the values are. They're all given up top. So it's hard to see, but up here it says that f of 4 is 2. So if f of 4 is 2, I'm going to plug in the number 2 there. G prime of 4, that's the number 5 right here. So I'm going to plug a 5 in where g prime of 4 is. G of 4 is right here, it's -1, and f prime of 4 is 3. So I'm plugging in all the values they gave me where they belong in the rule, and I get 10 plus -3, or 7. So you have to know the rule in order to do these general problems, because you're not going to know what the function is itself. So you have to write it in general and plug in the values, meaning you need to know the power rule, the product rule, and the quotient rule, all in general. And then on Wednesday, when we learn another rule, we'll add that on. But those 3 rules, if you know them in general, write them down in general and plug in what's given. So those are the problems I would have gone over in class on Tuesday. You can use them to help with your homework, which is section 2 for day 2. And I will see you Wednesday.